Alright, in this activity we're going to do temperature control of a stirred reactor. We're going to manipulate our objective, which is to maintain temperature in order to control a concentration out. So we have A coming in, we want to minimize A coming out, so maximize the conversion of A to B. And so we'll do that by controlling the cooling jacket temperature. So you can see right here, because the analyzer for product B is not fast enough for real-time control, it is desired to maintain the temperature at a constant set point that maximizes the consumption of A, so the highest possible temperature. So we'll go ahead, we'll first fit an FOPDT, and we'll go from there. Actually, let's just look at what we'll do. We'll first do a doublet test for an FOPDT fit, then we'll go ahead and actually fit it. We'll design a PI or PID tuner controller, and then we will implement it and tune it. And then it's left to you if you want to create the lowest concentration possible, or control for that lowest concentration possible. So we'll go ahead, we'll do a doublet test first. We're going to fit for these three parameters: the process gain, time constant, and dead time. So we'll go ahead for our doublet test. We have our steady state conditions, which are used for the initial conditions and as deviation variables. We'll store those within x0 as like the steady, as in the state for like the next step, the initial state. We also have our u's, which will be the initial condition for our manipulated jacket temperature. We have our feed temperature and our feed concentration. We'll go from 0 to 25 with spacing of 10 points per minute, and we're going to store the results within these arrays for CA temperature and U, which is the jacket temperature. We'll manipulate the jacket temperature to do a step test. We'll simulate our CSTR, and then we'll go ahead and we'll save it in this data.txt. Finally, we'll plot the results. So as we can see on the right, we have this step test. We'll go ahead and run the section just to make sure that's current. So there you go. On the top we have our manipulated variable, our jacket temperature changing, and then we have the concentration of A changing, as well as the difference in temperature changing. So as the temperature goes up, there's an inverse relation. Concentration of A goes down. Now we're going to look at designing a PI or PID controller. So we're going to go ahead. First thing we want to do is we want to actually solve for those constants. I went ahead and I did that down here. So we're going to read our matrix. We're going to get n's, which is the length of T. So the length of how many rows we have within our matrix. That's a good way to think about it. And our dt, the time difference between each one of those. Finally, we'll have our U fit, which is an interpolated value for our input variable. Here, that's the jacket temperature, and that's so that we can fit the dead time well. We have our initial guesses for the gain, the process time constant, and as well as the dead time. And we'll go ahead. We see that our initial objective is about 1650, and that's in units of some squared error. In fact, let's come down here. Let's look at our CSTR function as well as a couple of the others, so we have an understanding of what's going on. Our CSTR function takes the input, it has three inputs. The first is just the temperature of the cooling jacket. That's our manipulated variable. And then we have two states: the concentration of A in the CSTR and the temperature within the CSTR. We have some parameters: the volumetric flow rate, the volume of the CSTR, density, heat capacity, and the heat release during the reaction. We also have this E to over R, this activation energy normalized by the universal gas constant, and the pre-exponential factor. We have these right here so that we're able to use the Arrhenius equation to determine the reaction rate. Finally, we have UA, which is the heat transfer coefficient and the area of this reactor. So our reaction rate we'll determine here using the Arrhenius equation, and then we'll calculate the concentration derivative based on the fact that concentration in over minus out minus RA. The area is always going to be the same, so we just have this volumetric flow rate and then this change based on whether it's feed, the difference between the feed and the concentration within the reactor. We're assuming it's well mixed. We also have this negative minus RA as we take out the amount that is reacting at any given time. We also have the calculating the temperature derivative, and here we have three components. First, we have that portion similar to before, the difference that's happening just because of the mass balance, the mixture of what's going in and what's going out, and that it's well mixed. We also have heat released due to the reaction, and then we also have heat transfer with the cooling jacket. Finally, we'll return x dot, which has two values. It's a column vector with values for the concentration and the temperature, or derivatives, I should say. Similar to before, we then have our FOPDT function. You'll notice this one accounts for the dead time by interpolating. Then we'll simulate the FOPDT model given all the inputs using ODE 45. And finally, we have our objective function, which uses SimModel to simulate the model given the dead time constant, or given the process parameters, and fit for those process parameters, manipulating the simulated model and the actual model until they line up. So we'll come back up now. Okay, here we go. Here's where we implemented that. We have all our arrays. Let's make sure that we did this. I want to just make sure I'm referring to the right place. So we have a doublet test. We talked about that. Here we go. We're going to solve for our initial objective. We're going to use fmin search to solve for our process time constants. We go ahead, we get a process gain of about 2.15, and that's in units of change in concentration, or change in temperature internally versus change in temperature externally. So change in temperature within the reactor based on change in temperature of our cooling jacket. We also have our process time constant, which is about 0.9, and our dead time, which is about 0.08. And we compare those model functions here within this graph. You'll notice our initial guess, the main thing with our initial guess is that it doesn't account for the process time very well. We account for the process time, the degree to which the FOPDT fit does could be optimized. We probably could tell the solver to take longer to solve, but it does a good job. So the gain is a little bit off, is what I try to say, but the process time does a good job of approximating the behavior. We'll go ahead and we'll implement a PID controller. The first thing we'll do is we have these tuning constants. I'm going to go ahead and take out the semicolon so that we're able to see what the actual outputs are. And then we're going to look at how well it performs. To do that, we have our initial states and our steady state conditions again. We initialize the variables for the controller output, for the process variable, for the error, integral of error, derivative of error, actually it's derivative of the process variable, and proportional integral and derivative portions of that PID equation. And finally, we have our set point, which we initialize to 300, 320, and 280 to do a little bit of a step test. Then we have some limits for our output, and we go through and we do what we've done many times now, where we calculate the change in time, we calculate the error. If we have more than 1 point, we'll go ahead and we'll calculate the derivative of error and the integral of error. Notice it's actually the derivative of the process variable, so we'll use the negative of this within our derivative equation. And then we calculate the proportional, integral, and derivative portions, as well as the whole PID equation. Then we'll do some anti-reset windup and clip our outputs so they make sense. And we'll simulate those outputs with ODE 45. Then we set the very last value equal to the second to last value, just so that we don't have some weird discontinuity at the last point. Then we go ahead, we save that output, and we graph it. So we'll go ahead, we'll run the section. So let's come up here. Let's make sure we ran this one. I don't think we did. So we'll go ahead, run this section. You'll notice this is much higher than what we had before. We were at 16, now we're at 18. because it's optimizing it. So these were the initial guesses. Now it's optimizing it, and we'll see a better objective, as rather than just having the initial SSE objective where it was the final one, we're going to actually do the fitting. Alright, there we go. We're much closer. In fact, we're doing pretty good. So now we'll run this section, the next section. What do we call theta? So our theta was capitalized, capital T theta. So we'll go ahead and we'll implement that, and then we'll run this section. You can see we're all over now. That is not ideal. So what could be causing this? Let's come back up. Generally what I like to do first is just start with a lower gain and a lower derivative control. Those are what I found. And actually usually when I start tuning, I usually take out the derivative control. And so let's just take out the derivative control, see what happens then. We accidentally went through it all. One nice thing is I programmed here is that if Km, tau p, and theta p exist, it shouldn't go through and do the minimization. Unfortunately, we did I believe we did clear out, close all at the very beginning. No, we didn't. So we'll get here in just a sec. One is we have our controller. Now we're going to start looking at the output. We're going to design that controller. Or I should say we've designed the controller. Now we're going to tune it. So here we go. Here's the temperature set point, and we're tracking that. You can actually see we do a pretty decent job. You can see how the concentration within the reactor changes. As we have lower temperatures, obviously less of that reaction is going to slow down, so we're going to have a higher concentration of A out. You can also notice the jacket temperature. You'll notice some spikes as it, in the proportional term, initially spikes upward to help achieve that change. Go ahead and we'll uncheck this. We'll make it a little bit less. And then we'll see that we have this capitalized T again. So this last portion is where we start tuning. Go ahead and run the section. This last section is where we start tuning. You notice this is way off, or something's odd, for sure. So first thing I'm going to do is I'm going to look at C. Derivative control is equal to 3. That's not what we had before. So let's look what we had before, because that was doing pretty well. Derivative control was 0. Tau C was equal to 0.1 times tau P. So let's compare that down here. So let's just say derivative control is equal to 0.1. We'll go ahead and run the section again. So we're doing good, and I like how that looks. There's a little bit less oscillation, which is nice. It's what derivative control is designed to offset. So we've used these tuning correlations, and then afterward we start playing around with the parameters with our PID controller. The main points of this exercise are first, backing up and being able to consider how we start this process. We use the FOPDT constants to have an idea about how our process works, and use those constants to inform the tuning correlations. These tuning correlations are just starting points for our final tuning, where we manipulate them to change what how our controller performs. The thought here is that each process will have different priorities. If we're doing some biological or protein-based process, we're going to want to focus that we don't denature our proteins more than just having a fast result. If the fast result is what matters most, we're going to focus on that. And so with each one, we evaluate what our priorities are, but these tuning constants are a good place to start. You'll see here we've manipulated our temperature constant, so that we've manipulated our controller so we can track our set points. The last portion would be then going ahead and fitting it so that we have the reactor has a maximum allowable temperature of 400 degrees Kelvin, tuning our controller so that we never go above 400 degrees Kelvin because we don't want a runaway reaction, but how we can get just close to there without having that maximum allowable temperature and the dangerous runaway. So now you may implement derivative control as well. So I'll let you implement that. Hopefully this has been a good exercise in looking at how you program it from the start, and also looking at the portions of a controller that are necessary as far as measuring, and then evaluating what the controller output should be based on that measurement, and then implementing that output, and then waiting, and then iterating once again.